Hello and welcome back. My name is Amr Kamil and I will be your presenter for this part of the tutorial. So we'll start by looking at the solution for exercise 1. And again, the goal is to have each process print hello to a file, but have them appear in order of rank number. And so the way we need to do that, looking at the solution, is we need to have a loop that iterates over the rank numbers and have each process print out when the iteration count reaches its rank number. But we also need to prevent the processes from getting ahead of other ones. And so the way to do that is to put a barrier somewhere in this loop. Now you could put it at the beginning or the end. Here we put it at the beginning. And what a barrier does is it prevents anyone from moving forward until everyone has reached it. Okay, so again, in each iteration, nobody can proceed until everyone hits that barrier, and then the processor whose rank corresponds to the iteration can go ahead and print out their message to the file. And on some systems, we also need a sync call to flush the output to the file, so that when the next process actually prints, the output is already there. The main point of this exercise is to demonstrate that we don't get free synchronization. All the processes are running the same code image, but they're not synchronized in any way. And the only way that we get synchronization is by explicitly asking for it. In this case, we used a barrier to do that. And we'll see that a similar thing applies to other operations as well. Okay, then moving forward, let's take a look at some basic UP++ features and how to make use of them. So the first one that we'll look at, sort of one of the most fundamental features of UP++, is a remote procedure call. And the idea here is that we want to move computation to data rather than the other way around. So we'll look at an example where we want to compute some area function, which takes in some arguments, and it returns the product of these two arguments. Okay, so something this simple, of course, isn't something that you would do in a real program, but we're using it here for illustrative purposes. Okay, so to launch an RPC over to some target process P, we use the UPCXX RPC function, and we give it the target process as the first argument. We give it the function as the second argument, and then the remaining arguments are whatever the arguments to that function are. So in this case, we might have some local variables A and B that we want to send along to process P. So then what this does is that it launches over the RPC to the target process, and the way it does that is it sends a message with a reference to the function. Now it doesn't actually take the code for the function and send it over. Remember, each process is running the same code image, so if there's an area on the source process, there's an area on the target process as well. Okay, so instead we do some translation under the hood and pass a reference to that function. The arguments get packaged up as well, and so this combination gets enqueued on the target process, and at some later point the target process will actually execute the function, and if there's a result, it will send that result over to the source process. If there's no result, then it'll just send a notification that the function has been executed. What the source process gets back is something called a future. It doesn't wait. RPC doesn't wait until this entire process completes before returning. Okay, it's an asynchronous operation, and we get back a future that represents completion of that operation. We'll talk more about a future and how to use it, but sort of the simple thing we can do right now is to wait on the future, and then that gives us back the result of the function call. With RPC, we can rewrite our hello world, and this time we don't actually have to use files, because what we'll do is we'll actually just have a single process do all the printing. So that way the output shows up in the standard out. Okay, well, so we'll keep our ordering. So here we still have our loop, and we still have our check to make sure that so that each process prints in a separate iteration of the loop. And now what we do is we send over an RPC to rank 0. And then the function here, this is actually a C++ lambda function. Okay, so if you're not familiar with lambda functions, it's an anonymous function. It looks similar to a function definition in C++. The main differences are there isn't a name. Okay, it's anonymous. We have these square brackets here. There's something called the capture list for capturing local variables. Here we're not actually capturing anything, so it's empty. And there isn't a return type here either. Okay, that gets inferred. And in this case, if we take a look at the body here, it doesn't return anything, so the inferred return type is void. We have our lambda as our function we want to run on process 0. It takes an argument, so we need to supply that argument as the next argument of RPC. Okay, so in this case, each processor is sending its rank number as the argument for this function. We'll also make sure that the RPC completes before continuing onward. Okay, so again, a reminder, this is an asynchronous function. So if we want it to finish before proceeding to the next iteration, then we actually need to do a wait. Okay, and then as before, we need a barrier to make sure that nobody goes on to the next iteration until we're done with this one. All right, so I mentioned that what you get back from the RPC is a future. It doesn't wait for the entire execution to complete. It's an asynchronous operation. So a future represents a computation that may or may not be complete. And if we want to wait for the operation to be completed, then we call wait on it. And so what that does is it causes the current process to wait until the point at which the future is ready, at which point wait returns in and the current process can continue. So if we actually break up this RPC call, so previously we called wait directly on the result. If we just take the result of the RPC call itself, what we get back is a future over here. And a future is actually parameterized by 0 or more value types. In this case, for RPC, the actual argument type is the return type of the function. However, in this case, we have a void return, so we actually have an empty future as a result. Now, because this is empty, this future doesn't track a value, but it still does track the completion of that operation. Okay, and so we can go ahead and call wait on it to make sure that the operation is completed before moving forward. Okay, a little bit more on a future. So in general, it represents the readiness of some operation as well as some resulting values. Okay, and again, this can be 0 or more, as we saw in the previous case when it was 0. Okay, so a future essentially it contains a reference to some data structure representing the asynchronous operation, and so that data structure tracks two things: whether or not the operation is completed, and we see that with this ready bit over here. And then also whatever data values that the operation produces. Okay? And so in this case over here, the one that's illustrated over here, we actually have an int value. And so that corresponds to a future int. And then if we call wait on it, what that does is it waits for the operation to be ready. And then it also gives us back the result as part of the return. So in this case, if this was the underlying data for the operation, then result would end up being 3. Now, wait is just one way of managing dependencies. Okay, so in our particular case, we needed to make sure that our RPC completed before we moved on to the next iteration, and so we used wait to do that. We'll see later that there's also another way of managing dependencies, which is attaching callbacks to the result of an operation. And so there's a then method that allows us to do that. Since something like RPC is an asynchronous operation, we normally don't want to immediately wait every time we launch one. Instead, what we want to do is we want to overlap multiple operations, either communication with communication or communication with computation. So let's take a look at a basic example of doing that. So here what we have is we have a vector that's keeping track of multiple futures. And what we'll do is we'll launch several operations, each of which gives back a future, store them in the vector, and then we'll wait on them after we've launched everything. Okay, so here we're actually launching an RPC to every other rank. And we'll just make it simple over here and just have the RPC return the rank number of the target process. Okay, and since the return type is int, we get back a future int. And then we go ahead and store that in our results vector. Okay, but notice here that we're not actually waiting on anything. So it's not necessarily the case that any of these have completed before the next one gets launched. What we're doing instead is afterwards we'll go through our vector and wait on each individual operation, each individual feature, to ensure that each operation is completed. So this is just illustrating overlapping by being able to launch multiple asynchronous operations that can actually execute concurrently. But we'll actually see that there are better ways of waiting on groups of asynchronous operations. Normally speaking, we wouldn't actually construct a vector of multiple features, except in rare cases. So as a more complex example, we'll take a look at a 1D 3-point Jacobi stencil in UPC++. And what this algorithm does is that it operates on grids, and it's an iterative algorithm, so in each iteration it computes a new value of each grid cell. And that new value is a function of the old value of the cell and those of its immediate neighbors. So we'll stick to 1D in our examples just to make it simple, but the same principle applies for higher dimensions as well. Since it's a Jacobi iteration, this particular computation requires two grids. One grid where we're computing new values, and the other one that has the old values that the new values that we need to use in order to compute the old values. Okay, so for instance over here, if we look at how that computation happens, we see that the value of the new grid at index I is dependent on its old value and also the old values of its neighbors at indices I-1 and I+1. So we'll assume that we've distributed our grid across all of our processes. This illustrates distributing 12 elements over 3 ranks. And so these are actually shaded in green in the middle, the actual elements. The other thing that we'll do is we will also maintain ghost cells, which are copies of the elements on our neighboring processes. So the edge elements on our neighboring process. So for instance, over here, process 0 has a copy of the edge element, the left edge element of process 1. And we'll also work with a periodic boundary condition. So process 0 on the left-hand side also has a copy of the rightmost element of process 2. Now, not all of our versions of Jacobi will actually make use of these ghost cells, but all of our examples will have storage for those just to make the computation the same. And the only thing that will be different is going to be the actual communication pattern. So let's take a look at a simple boundary exchange. So what the algorithm needs to do is at each iteration actually needs to exchange boundaries so that we get the new values of our neighboring ghost cells that we need. Okay, so we'll do that using RPC in our first version. So if we assume that we have global variables old grid and new grid, and we have a function, just a top-level function called getCell, that takes an index and produces the cell value at index I out of old grid. What we can do is we can launch an RPC to our neighbor to invoke getCell and give it the actual index as we want as the argument. And getCell, it accesses it can access a global variable just like any other function. So it actually looks up the value of that cell and returns it. And again, what RPC does is we get back a future that represents the result, and we can wait on it as we're doing over here to wait for the operation to complete so that we get the resulting value, in this case, the value of the cell. Now I'll mention that from here on out, we'll generally elide the UPCXX : qualifier just to make our slides a bit more readable, but we'll still maintain that UPC++ names are in red and underlined. In terms of which index we need to pass for getCell, if I'm looking at process 0, in order to get the value 5 over here, it's actually at index 1 in process 1, and that's because process 1 is storing the ghost cell from process 0 at index 0 in its own copy of its grid. Okay, and similarly, on the other end, if n is the size of the local grid, then n-2 gives us the right edge of our neighboring process over to the left. So putting those two together, here we're launching RPCs to both of our neighbors. Again, the n-2 element of our left neighbor and the index 1 element of our right neighbor. Now what we can do is we can launch these RPCs at the beginning of an iteration, and here we're overlapping those two communications. But at the same time, we haven't waited, so we can actually do our interior computation. So if we look at our grid over here, everything but our own edge cells, we can actually compute using just local data. So we can do the computation for those interior cells, and then after that computation is done, we can go ahead and wait for the results of our RPCs and perform our edge computations as well. Okay, so in this case, we actually put the weight directly as part of our expression for computing each of our new values for our edge cells. And again, what we get out of here is not only just overlapping communication with communication, but also with the full interior computation as well. So taking as much advantage of asynchrony as we can. I mentioned that this Jacobi computation uses two grids, one with the values of where it's computing the values of new cells, and then one where it has the values of the cells that were computed in the previous iteration. So one common thing that a Jacobi implementation does is actually just reuse those same two grids. Okay, so once we finish computing an iteration, then it becomes the old grid. And then what was previously our old grid, we don't need that data anymore, so we reuse it for the new grid for our next iteration. Okay, so we do a swap here to swap those two grid pointers. Now, one of the things that you might notice here is that since we're reusing these grids and we're swapping them, there's a race condition between the swap happening and other processes RPCs completing. So if, say, process 0 ends up swapping these grids before its neighboring processes RPCs actually grab the data, then they'll actually get the incorrect data. So this is something that we refer to as a race condition. And again, just like we saw with our exercise 1 hello world example, if we want synchronization, we need to ask for it. Okay, and this is actually one important feature of one-sided communication, is that we decouple data movement from synchronization. And as opposed to two-sided messaging where we get synchronization whether we want it or not. With one-sided, if we don't need the synchronization, then we can avoid it. We can also amortize synchronization over multiple messages in some cases as well. And that actually comes into play in higher dimensional Jacobi computations. So what we want is we want to avoid having a straggler process so that we end up getting an incorrect value from our Go cell exchange. And of course, this behavior is unpredictable and may or may not be observed in testing. So it's something that's actually relatively difficult to debug. And so we want to ensure that we have the appropriate synchronization to prevent this. So the simple fix is similar to what we saw in exercise 1, which is introduce barriers. And so here we're introducing barriers, two barriers around the swap. One to ensure that the RPCs from the previous iteration, or from the current iteration, are finished before we do the swap. And the second one to ensure that we do the swap before the RPCs for the next iteration. Now, again, this is just a simple solution. It's not necessarily the best solution. And in fact, there are ways of reducing the number of barriers or using barrier-free synchronization as well. Okay, the important point though is that, again, if we want synchronization, we need to ask for it. So what we illustrated here was RPC and also asynchronous communication and how to overlap communication and computation and what a future represents. So RPC is one of the two fundamental communication operations in UPC++. And again, we use it to move computation to the actual data. The other fundamental communication operation is one-sided put and get. And this is where we get the PGAS model for UPC++. So UPC++ provides APIs for one-sided puts and gets, and then the implementation uses the fastest available network protocol. So if the network itself supports remote direct memory access, then UPC++ put and get uses that. If not, which is the case for some legacy backends such as MPI and UDP, then it's implemented without RDMA. But we still have, in either case, we have the same programming abstraction. So UP C++ actually provides two versions of rput and rget. The scalar versions, which are used to put and get a single element, and then vector versions, which are used to put and get sequences of elements. So taking a look at the scalar version first, the rget, what it takes as an argument is a global pointer, and that global pointer may reference data on some other process. So if we invoke rget on it, it initiates a one-sided get operation. And as with RPC, this is an asynchronous operation. So we don't actually wait for the data to get transferred before rget returns. Rather, we get a future that encompasses that data value. So in this case, we invoked rget on a global pointer event, and so rget gives us back a future int. And then, like any future, we can wait on it to wait for the operation to complete, and then we get the result of that operation as the return value of wait. For rput, we pass the value that we want to transfer as the first argument, and then the destination address as a global pointer as the second argument. So in this case, we're putting the value 42 over to at the memory location referenced by the global pointer called remote. Now, rput itself doesn't actually produce a data value to the caller, so we don't actually get an argument inside of this feature. We still do get a notification that the put has completed. So we get an empty future here. And then we can wait on it to ensure that the operation has indeed completed. So for the vector versions, it's similar, except for now we're giving it some source address, some destination address, and also a count of the number of elements to transfer. So in the case of rget, the source address is a global pointer, again, potentially referencing something remote. The target is a local pointer on the current process, and so that's just a standard C++ pointer. And then the third argument is the count. So what this does is it initiates a one-sided get operation to transfer data from this potentially remote location to the local location. And those data values get directly transferred into the target memory. And so rget doesn't produce a value. We just get an empty future that represents completion of the operation. For rput, our source memory is now located in local memory, whereas our destination is potentially remote. So the first argument, which is the source, is a standard C++ pointer, and then the second argument is a global pointer that refers to the destination memory. And as with rget, we also specify a count here. And again, what this does is it initiates a one-sided transfer of the data values from the local memory to the potentially remote memory. And once again, we don't get any values back as the result of the operation. Rather, we just get a notification that the transfer has completed. So we get an empty future, which we can then wait on to ensure that the operation has indeed completed. So now that we have one-sided put and get, we can go ahead and implement a version of our 1D Jacobi that uses it rather than RPC to do data transfers. But before we do that, we kind of need to see how the grids are represented and what we use as the source and destinations of these one-sided communication operations. So as we mentioned before, each rank has a portion of the grid, but also cells dedicated to the ghost region, where the elements actually live on the neighboring process. So if we imagine that each process has a grid pointer to its own local part of the grid, and also a global pointer to the start of its left neighbor's grid, and a global pointer to the start of its right neighbor's grid, then what we need to do is we need to transfer over this element, actually. So the second element from the right, which is the rightmost element owned by the left neighbor, that's what we need to transfer into index 0 into our own grid. And similarly, from our right neighbor, we need to actually transfer the element from index 1 into the last element in our own local grid. So if we assume that we have global pointers to the start of our neighbor's grids, and also, of course, we have a local pointer to the beginning of our own grid, what we can do is we can get a one-sided arget operation to obtain the ghost cells from our neighbors. And we could do either scalar or vector. What we've illustrated here is the scalar version. Okay, so notice here that we can actually do pointer arithmetic to compute a global pointer that actually points at the element that we want. Here again we have left grid pointers pointing at the beginning of our left neighbor's grid, and if we add the number of elements minus 2, we get to the actual element that we want. And arget, since this is a scalar version and we're working on a global pointer double, we get a future double, and then we can wait on that, which actually produces the double value, which we can then store in the appropriate location in our own grid. And similarly for our right neighbor. Now these two particular calls here don't do any overlap. When we actually get to the full iteration, we won't call it wait immediately. Instead, we'll ensure that we're overlapping these two communications with our interior computation as we were before. All right, before we do that, we'll actually take a break here for live Q&A. And then after that, we'll come back and we'll talk about some details in terms of how to set up storage so that we can actually do these one-sided puts and gets, and then we'll actually take a look at the details of the iteration using one-sided RMA. All right, so we'll break here for a few minutes.